right, let's start. Do you hear me?
Yeah.
Yes.
How are you doing?
Pretty good.
Good, good. So what I'm going to do today is to first show the solution of the homework problems, and then give some material on some mathematics, right? That's math which you should already know, but well, might have forgotten, and we will need it. So I'll just remind you what it all is about, and probably try to emphasize some things which are typically missed in trying to pass tests. All right, so homework problem. The first homework problem was about the sphere and a triangle on it. So there are some theorems about it, there are some formulas about it, and so forth. And many of you have actually found those formulas and used them, and it's okay. It's all fine. I don't mind you doing that, but in reality, this problem can be solved just by looking at it. So what you need to do? You have a sphere, right? And you have a triangle. So let's do some systematical analysis of what's going on if we have a triangle. We start with very small triangle. We start with very small triangle because if it is very small, then it takes only a very small portion of the surface, right? And remember that every surface, when you zoom in close enough, looks like a flat space. Right? So if you start, let's say, from here with a very small triangle, then it will look like a normal triangle, like what we can draw here. Remember that we live on a sphere, like it's our Earth, right? But we still can draw a triangle, and it's normal triangle, no problem about it. So it's absolutely normal triangle, and looks like exactly as what you studied in some geometry classes. But now we want to increase it. Right? In order to increase it, just imagine that triangle is made from I don't know, some film, and we take all those three vertices of the triangle, right, and start to stretch it. And all the time when we stretch it, what we will have is a triangle, like let's say this one. This is a new triangle, right? And so forth. And we continue stretching it and stretching, and every time on every step we see that those angles, each of those angles actually increasing. So the sum of those angles increasing all the time. So from there we see that we stretch it more and more and more, and the sum of the angle increasing more and more and more. So we continue stretching it, right? At some point we stretch it up to equator, whatever equator is on the scale, whatever we call equator, right? So that will be a triangle, and the triangle will be exactly on equator, because the sides of the triangle are the arcs of a large circle, and the triangle on the equator, that equator is a large circle. So this is our triangle. So that goes like here, then it goes like here, then it goes like here, right? But there is no reason for us to stop at this point. We notice that when we stretch it, the sum of the angle increasing more and more and more. So we keep doing it. Why would we stop, right? So we keep going on that, and eventually we'll come to the opposite point, right? So in the opposite point, what we will have, again, a small triangle. But now our angles here, right, they became those angles. Right? That makes sense?
Yes.
So now we need to compute the sum of those angles. So what we have, now remember that again, it's a small triangle. Small triangles look exactly as triangles which we used to, because any small, very infinitesimally small, it's an infinitesimally small triangle, and any infinitesimally small portion of any surface, if it doesn't have singularities, looks like a flat space. So what we have is a triangle, normal triangle, flat triangle, but we need to sum those angles. So if this is angle alpha, this is beta, and this is gamma, then what we have? This triangle, this angle is 2 pi minus alpha, this is 2 pi minus beta, this is 2 pi minus gamma. Right? So the sum of them is 6 pi, right? It's 2 pi plus 2 pi plus 2 pi, minus alpha plus beta plus gamma. But again, this is a normal triangle, right? So alpha plus beta plus gamma equals pi. So the answer is 5 pi. Right? And this is the largest one because, well, we increase it all the time and to this point where we cannot increase anymore. We came all the way. So that's it. That's the answer, right? So in order to do that, you don't need any formulas. You just need to play with things and see how things are going, right? That formula which many of you used for like how the sum of angles relates to this area. It's actually that formula is somewhat difficult to prove. I mean, it's possible, but it would require some work to do, and it's much easier just to look at this and see how it goes. Right. Now, if you have a hemisphere, then of course you do exactly the same thing, but the largest which you can do, the largest that you can do is exactly you need to stop on the equator. And when you stop on the equator, this is pi, and this is pi. So for this hemisphere, the answer is 3 pi. Okay? And it should be absolutely obvious that the answer for the hemisphere cannot be larger than the answer for the full sphere, right? Because we are talking about the largest possible sum of the angles, and a hemisphere is a part of a sphere, right? So if you got larger on the hemisphere, then that will be the answer for the full sphere also. But that would be the correct answer. Right? Any questions?
Hi. I was wondering if you subtracted points if we use the formula for number 1.
Not really. But if you got the right result out of it, then it's all fine.
Thank you.
The problem with the using of the formulas is that for some reason, a lot of people were stopping on the equator and saying that this is the area. Now, I want you to emphasize something in this in this problem, which is kind of interesting and actually has a lot of consequences in physics. In particular, the fact that the spin in quantum mechanics is quantized is well, it can be traced to the same kind of thing. Remember that we have a triangle here, right? It was a very small triangle. There is no difference between this triangle and the triangle which we started from. Right? It was infinitesimally small triangles, right? And then any point of sphere on the sphere is exactly the same as the other one. So the fact that we moved it over there doesn't really matter. The only thing which is important is to recognize that during that procedure we have to understand that what is outside is also a triangle. So we could just draw this triangle and count those angles, and we would get exactly the same answer, right? Right? So what is the reason for that? And if you think about it, that the reason for that is the following: there is no real good definition of what is inside and what is outside of the triangle. Now, when we on the plane surface, that distinction can be made. That distinction. So when I draw a triangle, right? It's obvious that this is inside and this is outside, right? But now you see that word obvious is a tricky one. You need to understand why is it so obvious. How do you know that this is outside? How do you distinguish? How do you label that? What is the property which tells you that this part is different from this part? from inside. And if you think about it, it's the following. That's a plane, right? Absolutely flat plane is infinite. So one portion, like if you think about it, that this triangle, any figure, in fact, splits all plane on two different parts. And only one part of that plane contains infinity. This part. And you call that part outside. The part which contains infinity. Right? This part does not contain infinity, right? Everything is finite. This part does contain infinity. And so there is a big distinction between them. You can always label what is inside, what is outside, because one part contains infinity and any other part would not. Right? That makes sense?
Yeah.
But now on the surface, the situation is completely different because there is no infinity. It's a compact, it's what is called compact surface. There is no such point as infinity. There is no infinitely far away point on the sphere. So there is no way to distinguish between outside and inside, and you have to treat them equivalent. And that's why when I draw a triangle here, it's actually not clear what I mean. The triangle is what is the inside, or the triangle which is what is outside. Both of them are completely equivalent. So you could answer this question without even stretching that film and so forth. Just looking at the triangle and recognizing that what's outside of this figure, what you think is outside of this figure, right? This part is also a triangle on this geometry. And so we need to just to count those angles here, and that's exactly the same thing. Okay, does that make sense? So that's the biggest difference. That's one of the biggest difference between compact and non-compact surfaces, right? That here is compact. That means that it has no infinity. Infinity is not included in there. A plane actually does have infinity, and in this sense, it's actually more complicated than a sphere. But it's flat, so it's easier for us to draw and to understand what's going on. Right? But that's the difference. And the fact that some surfaces are compact and some are not, it actually plays quite a huge role in physics. And it's very important part of recognizing, especially in quantum mechanics, that what your functions live on are actually compact surfaces. Compact space.
Professor, I have a follow-up question. So, could you clarify how you get 3 pi for the hemisphere?
Well, this is pi, right?
Yeah, I mean, how is it? Sorry, could you clarify how it is pi?
It's a straight line.
Okay.
Right?
Oh,
So
I see. Yes,
if you zoom in here, what you see is a straight line in the bottom.
that is true. It is pi.
So you see that I actually told you that in order to determine what angle is, right? So if you have on the surface, right, on some surface, you have two lines intersect. There is no way to define what angle is unless what you do is you zoom into this intersection point, and then what you have is a flat space, right, and two straight lines intersecting there, and then you of course can define what angle. So the definition of angle actually involves you to zoom in.
Okay. Also, Professor, so we're using the exterior angle instead of the interior angle for the full circle because the sphere is a compact surface. Is that
Right? Yeah. So it's,
okay?
because if it's compact, there is no distinction between interior and exterior. What is interior here for this triangle?
The interior is 180
Why?
degrees.
Well, how do you distinguish? You call this interior, I'll call this interior. And who is right?
I'm not sure.
There is no. That's what I'm saying. There is no way to distinguish between them. They're absolutely equivalent. what this part of the surface and this part of the surface completely equivalent. In a plane surface, they are not, because one of them contains infinity. And that's the distinction between those two parts. And then you can, of course, call one, use that names, interior and exterior. But here, when you draw on the sphere, you cannot use those names, because there is no way to unambiguously assign what is interior and what is exterior here. There is no property which distinguishes them.
Okay.
Right? So that there's the whole idea of interior and exterior. Actually, if you think about it, the whole idea of what is interior and what is exterior has to involve the idea of infinity, that there is infinitely far away point.
Okay.
Okay?
Thank you.
All right. So that was the first question. The first problem. The second problem was that figure. And you need to you should have computed its earlier characteristics. Namely, what involves here, you need to draw a polyhedron, right? And which corresponds to this figure, and then count number of vertices, count number of edges and number of faces of that polyhedral, and then compute chi, which is number of vertices minus number of edges plus number of faces. Right? That's what you're supposed to do. Now, I actually proved a theorem, right? Last lecture, or when it was lecture before, right? That first of all, that number does not depend on which polyhedral you actually draw. Polyhedron you actually draw. You can do whatever you want, and it will still be correct answer, as long as it approximates that polyhedron somehow to some degree approximates this figure. It does not matter which one do you choose. No matter what you draw, the answer will be the same. Right? That's the first theorem which I have proven. The second theorem which I have proven is that I have proven the theorem that it equals 2 minus 2g. Right? It's a theorem. So if you draw a polyhedron and you count those numbers and you count chi, and you got something which is not minus 2 for this particular figure, then you counted them wrong. Simple and clear. Because it's a theorem. That theorem exists for about 200 years. People have been working on it for quite a long time. This is not a counterexample of this theorem. There is no simple counterexample. There is no counterexample of this theorem. That theorem is as robust as you can imagine. So if you got something, that's actually very puzzling to me. Well, there are a few things which are very puzzling to me when I was grading that. First of all, that about half of the class draw exactly the same polyhedron. That cannot happen, right? Because there is no unique way to assign a polyhedron to this thing. Moreover, the answer actually does not depend on the polyhedron. So it's whatever you draw should give you a correct answer if it's done right. Right? Not. And half of the class actually made it, had exactly the same picture on their homework. Exactly the same polyhedron. Now, don't think that I'm stupid. I know how it goes, right? And what I'm trying to say is that this is a wrong approach, really wrong approach. Please do not copy each other's homework. In fact, I would really suggest you to stop working like in half of a class in the same place. Split on small study groups, 3 or 4 people, because you cannot talk to more than 2 people at once. So split on small study groups and do it on your own, each group. then you have actually chance to learn. Otherwise, you just copy somebody else results. And come on, try to figure out what is there any more idiotic way to copy somebody's wrong solution.
Could you show the picture?
What picture? Which
the picture that you said everybody, you know.
Like that. Well, and then some inside. Right? So they're not copied exactly, but that was the whole picture. And that picture is wrong. It's not a polyhedron. Because this face, the top face, this one, the top face, if you count it like one face, it has holes in it. If you just take this face, what you see is this picture, right? This is a face, this is a surface, and those two are holes in it. A face must not have holes. That was actually, I told you that on the class, right? And I actually emphasize that, and it's written on my lecture now. So please, if you have a theorem, right, and you get something which does not correspond to the theorem, that there is either one of two cases. That either you found that either you have proven, basically, one example is enough. If you have proven the theorem is wrong, right, or you made a mistake. And mistake is typically done not because you counted wrong those numbers. It's a simple counting exercise. It really doesn't matter. It's difficult to make a mistake there. Possible, but difficult. The mistakes usually are on the fact that you didn't apply all the conditions of the theorem. One of the conditions which is explicitly emphasized that a face must not have holes. So when you have something like that, what you should have done is draw, like, I don't know, a couple more edges. So now this is one face and it has no holes, right? And this is the other face and it doesn't have any holes either. And this is what, well, let's draw one here. That doesn't have any holes. So you need to split it on with edges, and then if you count in the new figure, you would get the right answer. It is -2. So please, I mean, see, if you copy someone else's solution, then it's really not useful at all. You see that I cannot really teach you, right? Only I can do is to provide the opportunity to learn. The learning part is your part. My part is teaching, your part is learning. Right? If you don't do that, well, it's a waste of time, really waste of time and money and whatever. I mean, why would you bother to do that? That's actually quite puzzling to me. So please just reorganize your work a little bit. Make small groups. Don't use large groups. It never works. Large teams do not work. The only way to make a large team to work is to split it in smaller ones. Okay, it's a simple organizational principle. Just keep in mind that the purpose of all of that is for you to learn, right? Otherwise, why bother? Okay, so let's come back. And what polyhedron can you draw? I mean, again, it doesn't matter which one. If you can draw, for example, this one. Well, let's do it. Less sloppy. For example, this one. And so those are the holes which go inside. So I don't know how to do it. Something like that. Well, it's a messy figure in this situation. So it's actually something which it's easier to do on your own than see somebody else results. And if you do that and you compute it, then what you get, well, I don't want to count, right? I mean, it's a simple counting exercise. The number of vertices here is 20. This vertex is, so you just count that number of points. Number of edges, again, you just count the number of edges. And remember that there is bottom edge and there is like some edges over there. And it will be 44. And number of faces here is 22. Right? Now you see that v plus f is 42 minus e is minus 2. And that's exactly as it must be, according to the theorem. Right? So that was a simple solution. It was actually, I always thought that it would be fun to play with. What is the fun to using someone else's polyhedron? I really don't understand. But it's a fun problem. You just can't play around with it, thinking about it as a play dough. I mean, come on. Physics is fun. That's why I'm doing it. If it's not fun, I would do something else. All right. So, getting that, and this is just an answer, but I want to tell you something more about it. And you see that what you do there, right? You simply count the numbers, right? You count vertices, you count edges, you count faces. And you, of course, have a requirement that edges is not interrupted, that faces do not have holes, and so forth, right? But after that, all you do is just count things. So, for example, if you have some edge, right? So this is one edge, right? But let me draw it differently. Let me draw it not a straight line, but like this. It's still one edge, right? No counting will be off. I don't care about how those edges look like. All I care about is that that's one of them. That's it. I just count them. I don't do anything else whatsoever. It's a simple counting exercise, right? That makes sense?
Yes.
All right. So let's use that new way of looking at it, and let's look at the sphere. Right now, let me draw a polyhedron here, which does not look like a polyhedron, but it is, because remember that we don't care about whether the edges are bent or not. So I put one point, I put it vertex, and I put one line, like a loop on the surface. So let me draw it a little bit better. So here's my sphere, right? I took one point here, and this is not an edge. Sorry. I don't know how to do it. Okay. I know. So let me use another color. So my polyhedron is I put one point here, and I put one loop on it, like this. So this is my edge. This is my vertex, and I have two faces. This face and this face. Right? So what I have here, number of vertices equals 1, number of edges equals 1, number of faces equals 2. Height equals 1 plus 1, no, 1 minus 1 plus 2. Equals 2. Right? That makes sense? So you see, you can actually do better than what I did. Like, don't consider cube or tetrahedron or whatever. You can draw very, very simple pictures, very simple figure. Let's see how it works on for the torus. All right, here's my torus, and so what I do, I put one dot here, 1 point, and now my first edge is going like this, goes around there. Is it clear? And my second edge goes like this. Okay? That make sense?
Yes.
So let's now count. I have vertices equals 1, right? number of edges. Remember, edge goes from vertex to vertex. So this is one edge, and this is another edge. So it equals 2. Right? Now we need to count number of faces. This is not. This is sort of not obvious here, but let's think about it. What face is? If you have normal polyhedron, what you think about polyhedron, right? If you take a knife and cut along edges, right? So what we get out is just a sort of plain figure, right? But again, remember that we are just counting, so it doesn't really matter that it's plain. It can be bent, whatever, but it's sort of piece of a surface without holes in it. That's all. Right? So let's do the same procedure here. Remember the procedures that we cut along our edges, and then see how much pieces we have after that. Right? So let's cut along this edge, right? And then and spread it like that. So what we will have is just a tube. Right? That makes sense? And then cutting along this edge is just cutting along this tube. And then I can spread it out, and what I see is just a plain figure. So it's one face. I have only one figure, right? So number of faces is 1. So what we have here is vertices plus faces minus edges I equals 0. Right? Exactly as it should. So let's try to do the same exercise on that figure. Remember that I had like 44 edges in previous run, right? So it's hard to count to 44. I mean, it's only little kids can do that easily. So what I do, I take my figure, right? And now I draw an edge which goes like this. Do you see what it is? So I sort of I draw an edge which goes from one hole to another, and then on the other side back. Just a loop. Okay, that's my one edge. Now remember that in order to count those faces, I need to think about that I cut along the edge. So if I cut along the edge here, I can spread that, right? And what I have is a torus with 2 holes in it. Right? Now I take the torus, and I cut it like this. This is my next edge. Then I take this torus and spread it. And what I have is a pipe, is a tube, right? Whatever we call it. Right? But that pipe will have that 2 holes which are connected here. One on one side and the other on the other side, like this. So those are holes in the surface of the tube. So it's still not a face. So in order to make it a face, what I need to do, I need to cut it more, right? So what I do, I then cut it along this. So here's my vertices then, right? And this cut on the pipe goes like this. Right? And then I cut like this. And this is this cut on the pipe. So now if I take this pipe, I cut it along this, I spread it out, what I will have is just one figure. One plane surface, right? So what I see here is the number of faces in this situation is 1. Now number of vertices is 1, 2, 3. Vertices is 3. And number of edges. So it's 1 edge from point to point, right? So I go here and go back, and this is 1 edge, 2, 3, 4, 5, and 6. And you count the chi here, and you got -2. All right. Does that make sense? So you see, with a little bit of better understanding what you are doing here, you actually can do things much easier. Moreover, this actually leads to a different view on the problem. It basically, that pi involves counting some non-equivalent paths, non-equivalent I don't know, loops on surfaces. And that's again another piece of mathematics which are quite interesting and quite useful and very important. And it talks about different surfaces and some paths, some loops on it, and you can now after that you can do some algebra on it, so you can actually make sense out of multiplication of loops and so forth. There are a bunch of theorems there, and then it leads to a better understanding of the topological structure of different surfaces. All right? Any questions about it? All right, then I move on. So the last problem was somewhat more traditional one, and but again, there is some message in it. And so the problem was that you had a boundary between pink and blue regions, and you had, let me do the same orientation. Yeah, blue is on top. So you had point blue on the blue region here. This is blue region, this is pink region, and you have some other point on the pink, and they were called point P and B. Of course, it's pink and blue, right? Now you have also the different velocities here. Velocity on the pink area is Vp, right? And the velocity on blue area is Vb. Right? And now you need to find out what is the path of the shortest time of travel. So you see that measure here is time. You need to minimize time, not distance. Those are different things, right? Time and distance, they even have different units. So the distance is, of course, is a straight line, no problem. But with time, you have to think and you have to compute it. And so what you then need to do, right? You need to find the path of the shortest time. Now, if you go from P to B, right, you have to cross this boundary. Again, this is mathematical theorem, right? And if you have a continuous path, you have to cross this boundary. So there will be some point of crossing, like this one. We don't know where it is yet. We just assume that it is. Now, after that, you need to go from P to point of crossing, and from point of crossing to B. Right? It is sort of clear that that's from this point to this to P, it should be a straight line. Right? Because here the velocity is constant and on this region, and the time is shortest if the distance shortest. Right? So this is straight line. And of course the same thing applies here, so this one is also straight line. And we don't know where that crossing point is, but it's somewhere on this line of a boundary. All right. So that's what we have. And now we need to compute where this point should be in order to time to be shorter. Right? Now, first of all, let's see that the answer actually exists. It's always a good thing to check. So there is a point where the time is shorter. Now, it's very easy to see, just considering the limiting cases. Let's take this point and move it very, 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 very far to the right. Right? It's sort of clear then that the further we move to the right, somewhere here, right? The further we move to the right, the more time it will take to go through this path. Right? Is it clear? Clear?
Yes.
So let's call this position x from say this point from when we put normal to the, and then if you try to plot time as function of x versus x, right? Then when we go all the way there, we see that it's increasing function, right? Now, if we go all the way over there, we'll have exactly the same thing. The further we go down there, the longer the time will be. So it means that somewhere here the function is also monotonic, right? So you have a function which is going up this direction, going up this direction. It's a continuous function, so somewhere it must have a minimum. So the minimum does exist. That does not prove that it's unique. It could be a couple of minima, right? And from this consideration, I cannot tell that it's 1 or 2 or 3 or 4 minima. But there will be at least one, for sure. Right? So we can try to find it. Now let's consider another limiting cases when we have when we still can be unsure. Maybe the right answer is just a straight line. So let's see that if it is so or not. And can we sort of see from the very beginning that it's definitely not a straight line? In order to do that, consider the following situation. What if the pink velocity is much smaller than blue velocity? Or blue velocity is much larger than the pink velocity? Right? It's the same thing. So you can travel on blue very fast, and you travel on pink very slowly. Now think about normal situation. Like say this is a swamp and this is like, I don't know, a ground. So you travel here very slowly and you travel here very fast. What would be the answer? What would be the most quickest way? What would you do?
You want to change mediums, or you want to go on the fast case as quick as possible?
Right, exactly. You want to leave that swamp as quick as possible, right? So what you would do, you go to shortest distance to the boundary and then over there. Right? And in the opposite situation, when this velocity is much faster than this one, then of course you do it the opposite way. You go almost straight here and then back. So we see that in two limiting cases, we see that the answer is definitely not a straight line. And then the answer should change continuously when we change the velocities. So in any velocities which are not equal to each other, the answer will not be a straight line. If the velocity is equal to each other, the answer is of course a straight line because there is no difference then between pink and blue. So then, now after all of this done, we can start calculating, right? So what we need to do is to calculate total time of travel as function of x. So if we call this as hp, this distance, and we call this distance hb, right? And that distance between this point and this point, right? This is the line which is perpendicular to the boundary, and we can call this one length L. Then what we need to do? Well, the total time of travel is time of travel on this stretch, right? Plus time of travel on this stretch. So we need to find that length. And that length is just hp squared plus x squared square root, right? That's this line, because this is Pythagorean theorem. And we need to divide it by pink velocity. Now we have this line, and its length is hb squared plus, now we need to square this one, which is L minus x. We take square root, and we put here 1 over v blue. this is time of travel from here to here. This is time of travel from here to here. So the total time of travel, I just need to sum them up. And this is exactly my function t as function of x. Time of travel as function of position of this point. Now I need to find the minimum of this function. So what I need to do, I need to solve the equation. The derivative of time of this function with respect to x to be equal 0. So what I have, then I take this derivative, and I have with 1 over Vp, then I have here x, and here square root of ht squared plus x squared, minus 1 over v ib, L minus x divided by hd squared plus L minus x squared squared. Right. So this is my dt over dx. And it must be equal to 0. That will determine my x. And so looking at this equation, so let me rewrite this equation using Blackboard trick. That's the same equation. Okay. I just look at this equation, and what I see here, this x divided by the square root, it's x divided by the square root, but by this length. This is right triangle, so it's actually sine of this angle. So this is theta p, which is exactly the same as this angle, right? So what I have here is sine theta p. And on this side, of course, I have this length divided by this length. So it is sine of this angle, which is exactly the same as this angle. So what I have here is sine theta p. And that's the answer, right? It's how those two angles, theta p and theta p, connected with each other. Does that make sense? Come on.
Yes.
For a second, I thought it didn't. All right. Now, as some of you correctly noticed, and I think everyone noticed, but only some of you actually wrote it. This is Snail's law, right? You did recognize it, right?
Yes.
But remember, the Snail's law is for light. It's how light travels. So light travels in such a way that it obeys the Snail's law, right? And you can actually prove that it obeys Snail's law by considering some phases of light propagation and so forth. I don't know how it was done in introductory classes. When I taught introductory class, I actually did prove it there. And I'm not sure if it stuck, but anyway, I did. And so it is a Snail's law, and it can be derived from the laws of propagation of light. So we know what light is, and we will learn about it, and we know how it propagates, and then we can derive the Snail's law. But here we have completely different story. We say that if we take a path from point A to point B, which takes the shortest possible time, then this path is also obeys Snail's law. Right? That's a completely different story. Right? The propagation of a person on the ground or on a swamp, right, is a completely different from propagation of light. So you cannot compare those two. Really, it's a completely different physical processes, and yet they have exactly the same result. Now, it can be coincidence. Well, it so happened. Who knows, right? But it's very unlikely to be, simply because the systems are way too simple. And when you have, in a simple system you have such strange coincidence, there is a big chance that there is a reason for that. But if you think about it, then it becomes very, very puzzling. Because if you shine a light from here, how does it know that light, light has no brains, no memory, never took any class in physics. So how does light know which path it should take in order to shorten the time of travel? That's kind of strange, right? The light cannot predict what will happen later on, and it cannot do such things. And yet it gives the same answer. Apparently it does know that. If you take this point of view, apparently that light actually can measure time and actually find out somehow what path gives the shortest. Right? It's something which completely cannot be answered, right? Because it's simply very puzzling. But the funny thing is that actually it's exactly what it does. And if you keep pushing like further and further on this direction, well, if you spend enough time on it, you will invent quantum mechanics. In quantum mechanics, that's exactly what light is doing. And it actually finds out the shortest possible, the path which takes the shortest possible time. All right, so it's and there is a mechanism how light can do that. I mean, it's not magic. It actually comes out of calculations. You can just write equations and find that that's what they give you. Always, that light tries to find the quickest way. All right. So, any questions? No. Okay. All right. Then I start to some mathematical stuff which will be useful, but it's also quite interesting in my point of view. It's fun. So now, what I told you pretty much everything about calculus, right? Already. I will go in a short way. But now it was I always was using just functions of one variable, right? In reality, we live in three-dimensional space and lost time, right? So our functions typically depend on four variables at least, like x, y, z, and time. And if you have more than one particle, then you have even more variables. Each particle has its own position, and so forth. So it becomes very so you need to consider functions of many variables, right? And it turns out that there is some distinctions between them, and there is something new which comes out with adding new variables to functions. And that's exactly what will be important, and that's what I want to discuss. So let's imagine that we have a function u as function of x and y. Right? It's a function, right? So if you draw it, x and y, right, and this will be u, then because it's a function, right? Function means that for each x and y, for each pair of numbers, you have only one answer, right? That means that it's a function. So then, what we have that function that for each x and y. So we take any point here, and we find u, right? Corresponding u. We take another point, we have corresponding u, and so forth. So that function will describe some surface. Here, right? If you try to draw that function, then instead of line, as usually, what we will have a surface. You know that, right? Right?
Yes.
Okay. All right. Now we can ask the following question. Let's take one point, and we know so this is my point x and y, right, with some specific numbers, and this then this height of that point is u of x and y of those x and y. Now we can ask, what if x and y a little bit. So what if I change x just by a bit? What will I have? So now this is my xy point, and this point is x plus dx and y. Right? I just changed a little. Right? Well, that's exactly. Then you see that I didn't change y, so I can completely forget about it. And what I will see then du, then the change. Du is a change, right? Then this point is come here, and that u will be a little bit different. So this is du, right? The change of the function will be just du partial derivative of u with respect to x times dx. Right? It's just normal one derivative. It actually tells you that one derivative, the derivative is the same. But now if I do different, if I go to different direction, to point which is will have x, the same x, but will have y plus dy. Right? It will also change. Function of u, right? So, and the change will be, of course, du over dy times dy. So here is the theorem then, that the total change for any dx and dy is this one. Sorry. Right? So now, no matter how I change it to each direction, each of those little displacement is a vector, right? Each of those little displacement vectors will have its own dx and dy, the components of displacement vector. And then I can always write find how function u will change for infinitesimally small displacement. And remember that it's enough, right? Right? So there are different ways to write it, and basically you can write it the following way. Let me introduce the vector of displacement, which has dx and dy components. Right? This is exactly the vector of displacement here. So that vector of displacement dr has a little dx and dy component. Right? That makes sense? So it's literally you stay at this point, and this vector tells you where to go and how long. It's a displacement vector. Right? Then I can rewrite this function. Okay, well, let me also introduce another thing. So that's one thing which I introduced, and the other thing which I introduced is a gradient of the function u. Sometimes it's written this way, sometimes it's written this way. Those are exactly the same. So it's just a change of notation. So this sign instead of equal, when you have three lines, it says equivalent. So it's not an equation. It just says this is exactly the same as this. It's just different notation. Right? Or and sometimes it's actually written even funnier. It's written as du over d vector r. I spent quite a bit of time telling you that you cannot divide by r, right? But this notation is not division by r. It's just notation exactly for the same operation. And this vector is just a vector of du over dx and du over dy. Right? So if you have function u, right, in every point you can find its derivatives and construct a vector out of them. And that will be a gradient. Then if you use that, we can write the very same formula as a gradient of u dot product dr. Right? Because that's exactly, this is x component of this vector times x component of this vector. This is y component of this vector times y component of this vector. And something. Right? So those are just notations, nothing else. Those three notations are absolutely equivalent. And that's what they mean. So when you see any of those, you can you should imagine that vector. By the way, there is also annotations which I actually like more. So instead of writing du over dx, sometimes we write dxu. Right? Again, that's exactly the same. If you see this, it means this. So you know what to do. Right? So those annotations, which it's just shorter, just the formulas look shorter when you use this notation. That's all. Okay, so this is that's object. This object is called the full differential of a function. Right? You know this, right? Right?
Yes.
Yes.
So the full differential can be written like that. If you have more variables, then you just continue going. It's called full differential. Good. For a function. Now I want to ask the following question, the different one. And remember that those are, when you take the derivative, right, it's another function. So those du over dx depends on x and y, and those du over dy depends on x and y also, right? It's some functions of x and y. So let me then write the following expression. I have some function which I called fx of x and y, and I multiply it by dx, plus some function of x and y, and I multiply it by dy. Okay. Such expression is called one form. And now remember that this is some function, right? We don't know what function u is, so we really don't know what this function is. And unless we define what the function u is to begin with. But now we look generally on them, right? So this is also some function of x and y. This is some function of x and y, and this is some function of x. Now I write similarly the same expression. This is some function of x and y times dx, and this is some function of x and y times dy. Right? But now I want to ask you if this expression is a full differential of some function. Is this expression a full differential of some function? Can you answer me? Come on, guys.
I don't think so.
Why?
Simply because you're limited to your x and y values. If you were to add another variable, I don't know if this is right. But I don't know if you'd be able to include it in like the previous variables.
Well, let's stick with just two variables for now. And in case of a lot more variables, almost the same. So it's actually not a big difference. But let's stick with just two variables, x and y. So I have this, right? Now, do I have, and I know that this is, if I have function u, I can write this expression, and it will be a full differential by definition, full differential of the function u. Now, I want to ask if I have some arbitrary functions, two completely unrelated, right? This is fx and fy, just two completely different functions. And I write some arbitrary functions here, and just multiply it by dx and dy. Will this be a full differential? Obviously, for some choices of fx and fy, it will. Right? Because that's what's written here is exactly what's written here. I just denoted this function by this one, and denoted this function by this one, right? So obviously, for some choices of fx and fy, it will be a full differential. But the thing is that not for all choices. So there is special condition on those two functions which those two functions must satisfy in order for this to be a full differential. And I explain geometrically what it means just in a second, but first I want to derive that condition. So let's start from the beginning. What do I actually ask? What am I actually asking? I'm asking if a function u of x and y exists such that its full differential equals this one. Let's assume that this function does exist. Then we actually can write its full differential. Here, it's already written. Right? Now, in order for that expression to be a full differential, we must have that fx of x and y equals du of dx, right? If such function u exists. And fy of x and y equals du over dy. Right? If this function exists, then this must be true. Right? But if this is true, let's now take this function f of x. Let me write it somewhere. Well, I don't have any place. Okay. Let's take this function fx and differentiate it with respect to y. Sorry, y. And according to this, it must be equal to the second derivative of u over dx dy. Right? That makes sense? I just differentiate this equation with respect to y. Now let me take this function and differentiate it with respect to x. Then what I will have is dfx, or dfy, sorry. Derivative with respect to x from here must be equal to the second derivative of u with respect to dx dy. Right? But those are the same things. So those must be equal to each other. Right? This equal to each other, so the left-hand side must be equal to each other. So again, we imagine that we assume that this is full derivative of some function. So a function u exists such that its differential equals this one. If it is so, then fx must be equal du over dx, fy must be equal du over dy. But if it is so, then df over dfx over dy must be equal to dfy over dx. Right? So if this is a differential of a full function of some full differential of some function, then those two functions are not independent from each other. They must satisfy this condition. All right? So it turns out it's the mathematical theorem again. It turns out that this is sufficient and necessary condition. So if it is a full differential, then this is satisfied, and if it is satisfied, then this is a full differential. So the full differential means that there is the function u exists. So let's see how it works on some examples. So let's start from the following one form. Y dx plus x dy. Right? that's exactly the same as I wrote before. This is now my fx, and this is now my fy. Right? So let's check if this satisfies. So we see that fx equals y and fy equals x. So we need to take fx and differentiate it with respect to y. dfx over dy equals 1. Right? Now we take dfy and according to our rule, differentiate it with respect to x. dx and equals 1. Right? So we see that it's they equal to each other. So this condition is satisfied. So this is a differential of some function. Now notice that this theorem does not tell us what function it is. It still requires some work to actually figure it out. But it tells us that such function exists. So we can spend some time and actually find it. Right? For this particular case, it's easy. U equals xy. If you now take the full derivative, you get exactly this expression. Okay? Does that make sense?
Yes.
Yes.
Now, let me tell you an example when it is not a differential. And I changed this expression just a little bit. I put a minus sign here. Right? And now what we have? We have our fx, that's the function which was staying in front of dx, right? It's still y. But now my fy, which is function which was staying right in front of dy, is minus x. Right? So now I take those derivatives and I see that this is minus 1. And so they do not equal to each other. And this condition is not satisfied. So there is no function u of x and y which would give this expression as a full differential. It does not exist. Simple and clear. If you try to spend some time to actually find it, then that time will be wasted because we know that it does not exist. It's a theory, right? We just proved. Does that make sense?
Yes.
Yes.
All right. So let me try to say geometrically what does that mean, all of this. And again, what I want to say is a lot of mathematical things, very natural in fact, if you look at them the right way. If you don't look at formulas, but try to find out what do they mean. So what does it mean that something the function exists or function does not exist? What follows it about? So let's consider what this differential means. That du equals du of dx plus du of dy dy. What does it mean? What does it tell you? It tells you the following: that there's those functions, that are just coefficients in front of dx and dy, right? And what it tells you is the following: that let's start with some point, and let's imagine that we know the value of the function at this point. Now let's move that point just a little bit along some dr, which has dx and dy as its component, right? Then this formula tells you how this function is changing, right? So it was this one, now it is this one. That's all. So if you keep going by infinitesimal small displacement, you will be able to find the value of that function everywhere. And that's the way, that's what it tells you, how a function changes when you change its arguments just a little bit. All right? Does it make sense?
Mm-hmm.
Now but then again, let's consider a form which is fx of xy dx plus fy x of y dy. Right? So we consider this form and we treat it exactly the same way. We say that let's imagine that we start with some point. So let me do it like this. Right? Again, so this is my x and y. And I say, well, I start with some arbitrary point here. With some value of something, whatever it is, I don't care. And now I use this as my rule to trace this is the full expression. So I start from here. Right? I change my dx and dy a little bit. Right? So I know that dx and dy just a little bit. And then I compute this expression, and I put a point here. Does that make sense?
Mm-hmm.
That's what I do, right? I start with some point, and then I use it as an increment of my point. So I change my position a little bit. I wrote that I know how this changed according to this, right? So I put in the next point here. I do it again, right? This is vectors on x and y plane, and I put it again here. I'm computing that increment and putting a new value here, and so forth, right? And that's exactly what I did here. Right? I can do it for a function. Here I don't know about the function exists. Here I do know, so there is a surface here, and that computing these increments, I just travel along the surface. But now there is the trick. See, let me take some path and come back to the same point. Right? Then, because it's just the surface, what I do, I trace the same loop here, and I will come back to the same point, right? So my u will not change if I just trace the changes of u of the function while I go there. It will change along the way, but it will always come back to the same place, right? Because I came to the same x and y, and u of x and y, the specific x and y is just some specific number. I always come back to the same number. That make sense?
Yes.
But there is no guarantee about it here. I can here, because all I do, I just compute the increments. When I come back, this line can go something like this on a spiral. Right? Because there is no a priori any function for which it is full derivative, full differential. So, and that's exactly the reason for that. So if it is not a full differential of some function, it means that if I go here around the loop, here I will not come to the very same point. It will that line which I will trace. I just explained you how I traced it, right? For each increment, I just put a new point here. So that line which I will trace here will come to some other point, right? Somewhere here. And then there is no function. Because that's definitely not a function, right? By definition. For one point corresponds to 2 points here. Does that make sense? So that condition which we have, the dfx over dy, notice that those are cross derivatives, right? dfy over dx. See that it's right? So this is a cross derivative. So that's condition that this never happens. That by the way, this function, that condition must be satisfied everywhere on x and y plane. Otherwise, it's enough for this condition to not to be satisfied in one point, and then it is not a function. If you think about it, the example of it, think about the screw like that. So take a plane and just screw it like that. Go up and up and up along some one axis, right? That for such a surface, right? That condition will not satisfy in one single point. Everywhere else it will. So that's what we will that's what it means geometrically. That really is not a function. So you go around. There is at least one such loop around an xy plane. When you go around it, the value of f of whatever you're computing there will not return back to its point, to the same point. It will go upstairs. So your typical stairs, for example, here is exactly that point, right? You may end up on the next floor. Does that make sense?
Yes.
All right, so that's what those things mean. And it's a full differential and so forth. We will use those things, and that's why I do it. I explain it to you. Now, I want to also introduce one more thing, and it's called a vector field, something which we will need. And so, again, that's sort of a separate topic, although they're very, very strongly connected with each other. And by the way, I will not be able to tell you everything which you probably would want to know about it, but I wrote a lot more in my lecture notes, so please read them, or any textbook in mathematics will have. So again, let's imagine an xy plane, xy, right? And let's say that, and we have a vector field. What does it mean, vector field? Well, let's say that vector field is two-dimensional. Dimensionality of space, dimensionality of vector field does not have to be the same, but that's a different story. So we say that there is a vector which depends on x and y. So what it means is that every point of this space, there is a vector. This one, right? So you change that point a little. You go to another point, and it's another vector. Right. So vector field means that in every point of space there is a vector. And this vector is also two-dimensional, so we can draw it on the same space. Right? Does that make sense?
Yes.
So such an object is called vector field. It consists of two functions, of course, because it's a vector. Then it has x component and it has y component. So basically, just two functions, and I can represent them as vectors. That's all. Okay, that makes sense. So now imagine the following construction which we want, I want to discuss. We have, let me write it a little bit lower. And we have this vector field everywhere, right? That vector exists in every point. And then we take some point A and B. So this is point A and B in our space. And we draw some path from A to B. So the space path is directed. You see that there is arrow here because I go from A to B. Right? It seems like I'm saying idiotic things, but trust me, this is important. The same way as like place must have no holes is important. Was important, right? The same thing is here. The fact that it's oriented path is actually quite an important. So let's call this path gamma. It is some path, it's somehow given to us. maybe just as function of y function of x, or whatever. It doesn't really matter how. Now, what I want to do is the following. I want to take this path. I want to split it on very small displacements. Instead of going through the path like that, I say that I go along this displacement first, then I go this displacement first, and so forth. Right? Then what I want to do, let me call this particular displacement dr. Right? It's a vector of displacement, so it's dr. It's a small one, that's why it's d, right? I take the increment. Now, in this point, it's the very same point of the path, right? Right here. It's a very, very small interval, right? So it's pretty much, I can represent it as one point. There is that vector f of x and y, of this x and this y, right? On the path. So I can take a dot product. I can say that f, to take dot product, that f of x and y dot dr. Right? That makes sense so far?
Yes.
So I have it for every small displacement. I compute this for every small displacement. And you see that for every small displacement, dr will be different, right? dr here is different than dr here. They have different directions. And vector f will be different because now vector f here was taken at this point. The vector f here will be taken from that in that point. So those things will be different from each displacement. But nevertheless, for each of them, I can compute them and then sum them up. Okay. And that's along the path gamma. So this is called integral of the vector field over the path gamma. That's now again. I want you to understand that there is no magic here. This expression means this construction. Those expressions tell you what to do. That expression tells you, take path gamma, split it on little intervals, displacements, calculate this for each displacement, and sum them up. That's what it tells you. Right? Formulas are not some sort of magical scribbles when you write something is happening. Write it on paper, something is happening. No, it does not. It just tell you every formula must tell you what to do. In this sense, formulas make sense. Right? If you look at the formula and you don't understand what to do, then there are two possibilities. Right? Whether you simply don't know that what it tells you what to do, right? Or the formula makes no sense whatsoever. Right? So this particular expression is describing this construction. So after that, and you see that the path gamma is very important here. The path gamma, that's what you start with, right? You draw a path gamma and you split it on and calculate this thing. If I draw some other path, like this one, right? Gamma prime. Then, and I do the construction for gamma prime, exactly the same thing. But it's now along gamma prime. So when I see this, I need to draw my gamma prime path, which should be given to you, otherwise it makes no sense, right? And then I need to split that gamma prime and do it the same. And for that gamma prime, you see that the value of the vector field on each point will be different. The r's will be different than for this gamma. So there is no reason to think that this is the same as this one. So they generally, they do not equal to And this is the following. Let's write this one in components. What I have, fx dx plus fy dy, right? That's exactly the product of two vectors. And now you can recognize that's one form which we discussed before, right? So if dfx over dy equals dfy over dx, if over dx, if your vector field is such that it satisfies this relationship everywhere, then this is a full differential, right? If this is satisfied, then we can say that there is a function u such that this is its differential. But then what we have here is just this differential. So in this particular case, only in this particular case, this equals, right? This equals integral of du, right? Because this one is du. But that's a function, right? And it's a full differential. Summing up full differential is just a difference of function u at point B minus function u at point A. And it depends only on B and on A. It does not depend on gamma, right? So if our field is such, that vector field is such that this is satisfied, then this expression, this construction, actually miraculously does not depend on the path. And then, again, this is very, very strong statement if you think about it, because the construction for different paths are completely different, right? Here you have this dr, here you have this dr, here you have this vector field, here you have this vector field, right? Vector. So you need to do on every step, every term will be different. This when you go along this path and when you go along this path. But if this relation is satisfied, then the value when you of this construction, when you use this path, will be exactly the same as the value of this construction when you use this path. I think this is absolutely remarkable. All right? That makes sense?
Yes.
In particular, you see that if we go one way here and the other way back, right? Then considering this as a loop, we end up at the same point where we started. Right? So this then has the same point. But then this is 0. So that's construction for a loop. It's sometimes written like this. F dr equals 0 if we have that f satisfies this condition. Now, for any closed loop, this integral will be 0. Doesn't matter which closed loop it is. Actually, this is exactly that previous theorem can be reformulated on the following way: that if such a construction for any closed loop is 0 for any closed loop, it's enough if there is one closed loop for which it is not 0, then everything is crashing down. But if for any closed loop this construction is 0, then this f will satisfy this relationship, and so there is a function u for which you can write this as a full differential. Okay, that makes sense. All right. Okay, so that's two mathematical statements which I wanted to tell you that what is differential, what the function is, right, and so forth. And it's quite an interesting to understand that. Remember that you were told about that the function is just for one argument. There is only one value and so forth. And you probably thought that it's completely simple and trivial things. Right? Who cares about? Why those professors tell you in such length about such trivialities? Those things are not trivial. They're very, very trivial when you have only one argument. When you have functions of many arguments, that becomes statements. Very, very powerful. Those things which we talked about, which we are talking about. Next lecture, I show you how they're used in physics in the simplest possible example in physics. And you see that a lot of things which you know, it actually follows exactly from there. It's not the consequences of those theorems. And but there are a lot more in physics which follows from those theorems. A lot of things in electromagnetism are followed by very similar constructions, which we will discuss later. All right. Any questions? Again, let me ask you for a favor to yourself. Please, if this looks very unfamiliar or familiar but you forget or you are not comfortable, please read it again. Find some textbook or Wikipedia or whatever, and or talk to your friends, not to 25 friends. Please talk to a few.
Professor,
Yeah.
what is the topic of this? What is it called again? I'm sorry.
Well, it's I don't know really. It's a common knowledge in my world. I live in a very special world. I don't know. Function of many variables, calculus of functions of many variables, full differential of function of many variables, something like that.
Thank you.
Right? So it's but again, it's I told you that that construction in any construction like that is called one form. Sometimes it's full differential, sometimes it's not, right? But there is a whole mathematics on top of that. There's one form, two forms, n forms, and then how to deal with that. And this is a lot of fun to. That mathematics is amazing, really amazing. And if you have any time, please study it. I mean, it's called differential geometry. It's unbelievable beautiful, and I wish I knew it. Anyway, any other questions?
Professor, I did have one question.
Sure.
So in terms of the path, so you said the path from A to B, the gamma path is the same as the other path if that expression in the bottom left.
No, not at all. The
I thought you said
value of the
the
integral is the same.
Oh, okay.
Path can be the whole idea is that if this is satisfied, then for any two gamma,
Yeah.
this will be equal to each other.
Okay.
So that's the whole construction does not depend on gamma. You can choose whatever path you want. Right? It can simplify your calculations quite considerably. You can choose whatever path you want, and for any other path, this integral will be exactly the same.
Okay. That makes sense. I just want to clarify that.
All right. Any other questions? All right. That's it then for today. Thank you.